Modern artificial intelligence faces a rigid mathematical paradox. A frontier language model contains a dense, continuously shifting interior manifold of billions of parameters. Yet, we attempt to govern this massive internal volume using only a few dozen sentences of human text, a thin, low-dimensional surface boundary. The industry standard treats this phenomenon as an emergent property of machine learning, or simply a pragmatic engineering hack to bypass human data labelers. But that assumption misses the underlying structure. The architectural determinism thesis posits that these models are projections of the doctoral research conducted by their founders. This perspective suggests that Anthropic's constitutional AI draws its structural logic from the ADS-CFT correspondence, a duality found in theoretical physics. To see how this works, we have to translate abstract physics into applied machine learning mechanics. If we want to understand how a system of this scale is actually aligned, we must abandon computer science metaphors entirely and adopt the mathematical language of quantum gravity and integral geometry. This timeline shows the intellectual convergence that built contemporary AI, splitting at 2009. That year marks the simultaneous doctoral completions of Demis Hassabis and Jared Kaplan. Hassabis completed his work in cognitive neuroscience at University College London. Kaplan finished his in theoretical physics at Harvard. Hassabis approached the problem of information compression biologically. His research defined the hippocampus as a construction engine that performs a bottom-up bind-in operation, assembling fragmented cortical data into a compressed spatial scaffold for mental simulation. This diagram illustrates the dual approach Kaplan took from physics. He examined a top-down projection, where a low-dimensional boundary dictates the state of a high-dimensional interior volume. We will exclusively track this right panel, the physics lineage, and how it provided the explicit mathematical blueprint for Anthropic's architecture. These laboratories are scaling 15-year-old doctoral frameworks onto modern silicon. This flowchart traces the physics ancestry into machine learning. The Hilbert space identity proves the complete quantum state space of a bulk volume equals its boundary. We map these directly. Multidimensional ADS bulk geometry maps precisely to a language model's interior weight space. The lower dimensional surface, the conformal field theory or CFT boundary, maps to Anthropic's constitutional principles. The connection between the two is defined by the GKPW relation. It establishes that boundary values specify the exact source couplings that deform the internal space. In machine learning terms, a constitutional text principle like be honest mathematically acts as an ultraviolet fixed point on the boundary, establishing the strict constraints for the entire system. There is, however, a critical limitation here. The GKPW relation is a purely static mapping. Local operators on the boundary lack the scale needed to probe deep into the bulk geometry. How does training actually reach in and update the deep weights? Proving that the boundary and the interior share the same state space is not enough to build a functioning AI. We need an actual dynamic mechanism to physically push boundary text into interior code. In 2016 and 2017, Samuel McCandlish developed a framework to bridge the gap between static boundary points and the deep interior. He utilized kinematic space, the space of oriented geodesics cutting directly through the empty interior volume of the ADS manifold. Translated to a language model, this represents the behavioral state space, the set of all possible output trajectories it can generate. Within this space, operator product expansions, or OPE blocks, function as localized scalar fields propagating along those trajectories. In the architecture of constitutional AI, these OPE blocks map directly to preference models. They act as aggregated evaluations of AI behavior, compressed into a single functional mathematical object. McCandlish successfully formalized how localized boundary data, specifically human preferences, can be packaged into distinct scalar fields capable of moving through the model's behavioral state space. The core dynamic mechanism comes down to a proof that the ADS Laplacian and the kinematic space Laplacian intertwine under a specific mathematical operation, the X-ray transform. This gives us the central architectural translation. Reinforcement learning from AI feedback, or RLAIF, executes the inverse X-ray transform. It smears boundary preference data across the deep weight space, deforming the interior geometry so unaligned paths are topologically disfavored. Subjecting a neural network to this kind of violent geometric deformation risks breaking its connection to the boundary entirely. To prevent this, the system requires the modular Hamiltonian constraint. In physics, this is mathematically identical to fluctuations in minimal surfaces within the bulk, generalizing the Ryu-Takayanagi formula. In the machine learning context, the modular Hamiltonian maps directly to the Kullback-Leibler, or KL divergence penalty used during RLAIF optimization. The KL penalty acts as a physical lock. It ensures that any geometric adjustments deep within the interior remain rigidly tied to the constitutional constraints on the boundary. Constitutional AI operates as a programmatic application of intertwining differential operators, forcing bulk geometry to obey surface laws. This theoretical alignment has a direct empirical consequence. It explains why constitutional AI only becomes highly steerable and predictably aligned at massive, billion-parameter scales. This chart demonstrates neural scaling loss. We see cross-entropy loss decaying according to a precise 0.076 power law. These machine learning power laws connect directly to statistical mechanics, structurally identical to critical exponents near a renormalization group fixed point. In physics, holographic correspondences and gauge theories require the large N limit to function correctly. Only in this large N limit does the internal geometry become completely smooth. The microscopic friction of discrete data tokens washes out, and curvature corrections are suppressed. Constitutional AI works better at scale because the system finally becomes large enough for the holographic physics to hold mathematically true. Under the thesis of architectural determinism, laboratory governance policies directly reflect these differing physical priors. DeepMind pursues agentic safety through mental simulation, teaching agents to evaluate consequences before acting. Anthropic pursues structural alignment by defining unbreakable behavioral state spaces at the boundary. As models reach toward general cognitive capability, safety depends on properties of integral geometry rather than simple algorithmic checks. Aligning superintelligence will ultimately depend on our ability to maintain well-behaved boundary Hamiltonians, projecting physical constraints securely onto the silicon.